section for us to cover here is about nuclear energy and the uses of nuclear energy, including nuclear power. If you guys read the article and answered the question, you should have a pretty good understanding about how nuclear energy can be used. We'll talk about it in some more detail here in our notes. And we left off here before break talking about this concept of a chain reaction. Could anyone tell me in your own words, like, what does that mean to have a chain reaction? You see it? Yeah, it's when the products of something sort of start the reaction happening again, which releases more of these products, which starts more of the reaction happening, basically growing at an exponential rate, increasing the rate of the reaction each time it happens. And we looked at this video of the mousetraps, right? You just drop a single ball in this plexiglass box filled with mousetraps, that trips one single or two balls which pop in the air, and they hit other mousetraps, which hit other, and pretty soon they've all triggered pretty quickly. Okay? That concept is called the chain reaction. And in nuclear decay, there are instances in which a radioactive element, when it decays, releases a particle which hits other nuclei, which causes them to decay, which release more particles, and this is what's called a chain reaction. Now, this chain reaction can happen in a controlled way, where you've built certain types of equipment to control the rate of this reaction, or it can happen in an uncontrolled manner. What do you think? When is it used in a controlled manner? Tyler? In a controlled manner? No. Okay, medication and nuclear energy, a power plant, the reaction is carefully and tightly controlled. If we allow a reaction to take place uncontrolled, that's what's used in nuclear weapons, okay? Because you have this explosive force. It's basically, once it's initiated, is unchecked. So we'll talk a little bit about nuclear reactors. These pieces of equipment that take a fuel source of a radioactive isotope and use that radioactive energy to generate electricity. So some important parts of a nuclear reactor, a nuclear power plant. One are the control rods, which you see here. Do you remember from the article, do you know what control rods do? Ellie?
They stop or slow down the chain reaction?
Yeah, they can slow down the reaction. These control rods can go, so here's like a diagram of them. These black, so the fuel are these red cylinders. These control rods can go down or they can be raised up. So here you see them raised up out of the reactor. What do you think happens when they're lowered?
It has to go through it in order to continue the process.
Yeah, so the particles being produced by this fuel rod cannot get to this fuel rod because they're blocked by this control rod, and that slows down the reaction. If they're taken all the way out, the reaction speeds up because these fuel rods can interact with each other. So that's the purpose of these control rods. They're usually made of substances that can absorb neutrons and other particles that are released by the reaction. Often that's cadmium or boron. And it's used to control the rate of the reaction. They're controlled so that as they're inserted between the fuel rods, they slow down the reaction. When they're withdrawn, the reaction can speed up. The entire reaction also takes place in a substance called a moderator. And this green sort of material is what the moderator is. And it helps to slow down the neutrons that are released in this reaction to make the reaction more controlled, to better are able to harness that energy being produced. So here's sort of a general drawing of how things work in a nuclear reactor. Obviously, they're much more complicated than this, but this is sort of a simplification. So you have the nuclear reactor is where the reaction actually takes place. That's what's shown here. These dark black rectangles, those represent the fuel. Here are the control rods, which can be inserted between those fuel rods. And then you have this loop. Because as this reaction takes place, what does it generate?
Heat.
Well, not electricity
Energy.
yet. Energy in the form of heat. Creates a ton of heat. And so what happens to the water or the liquid that's in this loop? It gets really, really hot. And that water is circulated, right? And it's used to boil water in another secondary water loop, and that forms steam. And anything you can do that can create steam can turn a turbine, which generates electricity. Turbines take rotational energy and turn it into electricity. Turbines are also used in a wind turbine. As the wind blows the propeller, it spins the turbine, generates electricity. They're also used to produce hydroelectric power, where you have a dam, and as the water is going through it, spins a turbine, which generates electricity. You could use gas, boil water, produce steam, to turn a turbine, generates electricity. So all of these things basically use the same idea. Spinning this turbine generates electricity. Another requirement in a nuclear reactor is water. Nuclear reactors are almost always built near a large body of water because they need to take in water to cool down the steam back into liquid water so that it can be processed again. So you'll generally see nuclear reactors built along the water. You'll see, if you think about like the Simpsons, that those huge towers that sort of are concave, those are cooling towers. Okay? The actual reactor, the nuclear reactor, is in a building that's well contained, usually made of very thick concrete, so that if there ever was an accident, radiation would be somewhat contained within this building. Okay? So the basics behind a nuclear power plant is the heat given off by the nuclear reaction boils water to produce steam, and that drives a turbine, which generates electricity. Colin?
Obviously the control rods are used to like slow down the chain reaction.
Yep.
Can you just like turn the thing off?
Yeah, you could shut it down. In
And then-
fact, the way these control rods, one way that they're often held, one thing that can cause a problem in a nuclear power plant is a loss of electricity to it. Because obviously raising or lowering these control rods, if they were up and the plant lost electricity somehow, then the reaction can continue uncontrolled. Often these control rods are held up by electromagnets, so that if they're held up by an electromagnet and that energy is caught, what happens to the electromagnet? It turns off and they disconnect and they go back down to slow the reaction again, stop the reaction.
Would the residual like heat and stuff continue?
For a while, but it would stop. The reaction would be controlled. They can shut it completely down. Yeah. So, does anyone know the benefit? Why? So, there is some controversy about nuclear energy being used to generate electricity. Some people feel we should use more nuclear energy. Some people feel we should use no nuclear energy. What are the benefits of it? Let's look at it from both ends. What's a positive aspect of using nuclear energy versus another source of energy? Abby?
It produces a lot of electricity.
A small amount of fuel produces a large amount of energy. Exactly, that's one. Count?
Unless something goes wrong, it's rather like a clean energy source.
Yes. It releases zero carbon dioxide and greenhouse gases. So there's no emissions of CO2, carbon monoxide, or other pollutants. Because those, what do those lead to? Pollution and global warming and climate change. That's what carbon dioxide is, a greenhouse gas that warms the earth. It's a major issue today. So they don't produce those gases, so that's good. How about on the negative end? Or is there anything else you can think of as a positive about using nuclear energy?
This is more of a question. Is it expensive?
We'll get there in a second. Anyone seeing, what are the negatives then? What's the downside of nuclear energy? If it releases very little pollution, so why don't we use it all the time? Because here?
If like the system makes or something, or to last and produce and stuff, like
Yeah. If there's a problem, there's what's sometimes called a meltdown. If the system is breached, the reaction goes out of control, it can release radioactive pollution into the immediate area. Does anybody know names of examples when that happened in the past? No, you read about it.
Oh,
Sean?
I know about one.
the 3 Mile Island.
Okay. That was a relatively minor one in comparison to some of the other major meltdowns. Tyler? The flash? Is the flash created from a nuclear meltdown?
Yes.
Yeah.
Oh,
Well,
Okay.
particle accelerator.
What else? How about in real life?
the Chernobyl incident.
Chernobyl? Chernobyl was in Ukraine,
Yeah.
and that was a nuclear reactor in the Soviet Union that melted down.
That was
And
like Wolverine.
any others? You got another one, Kasia? Fukushima, where was that? Japan. What caused that melt? What happened prior to that meltdown that sort of started the problem, Sean? An earthquake and resulting
A tsunami.
tsunami, which flooded the plant, destroying the controls to keep the reaction in check.
That's why you don't build one on an island.
So this is I'm going to pass this around. This is kind of interesting.
They had it covered.
So we can use oil or natural gas to generate electricity. So on this card is one single fuel pellet that it's not real. This isn't real uranium. But if it were, it's a model so you can envision it. This little fuel pellet here on this card, okay, that can produce the same amount of electricity as 3 barrels full of oil. 3 oil barrels like this, or a ton of coal. Okay, that amount of electricity you could generate in that little fuel pellet is equivalent to those. So, like somebody said earlier, a small amount of nuclear fuel can provide a very large amount of energy. A kilogram of uranium creates 100 trillion joules of energy. That's about 4 million kilograms of coal. So you could generate vast quantities of energy using nuclear fuel versus traditional fossil fuels. This is one that's close to us.
Oswego.
So this is around Oswego. And this is called 9 Mile Point. This is a nuclear power plant. It's built on the lake. Okay? That's steam. Yeah, so this is not. So this is not steam. This is not pollution coming out. This is just steam. When they cool down the fluids in the reactor, release the steam. They take in water from the lake, use it for cooling, and then that water is released as steam. Eventually falls back down and condenses. So this is in Oswego, New York. It's pretty old. A nuclear power plant doesn't last forever. Okay, this was built in 1969. It is still operating. It's the second oldest nuclear power plant in the U.S. Nuclear power plants were built mostly in the 1970s, and since, I don't know, the last 20 years or so, very, very few nuclear power plants have been built. They are extremely expensive from the outset to build, okay? And so they are often not, they're not very commonly built today. Sean?
So when you burn fossil fuels, it gives us the
Yep.
Did you put a turbine in the gas?
They don't generate usually high pressure emissions that could drive that. That's an interesting idea though. So the pros and cons. The pros of nuclear fission, which is what this is called, the breaking of large nuclei into smaller nuclei, doesn't produce greenhouse gases, produces high amounts of energy. Once they're built and running, they are pretty cheap to run.
Not cheap to build.
Not cheap to build, but cheap to run. Now we missed a big con that I should have mentioned earlier. So yeah, if it melts down, that's a problem. They are expensive to build. There's another problem, and that is what to do with the nuclear fuel once it is no longer usable.
That was my question, yeah.
So even after all of the energy that you can use for generating electricity has been harvested from those little fuel pellets, the material still remains radioactive and dangerous for millions of years. And the question is, well then, what are you going to do with it? And so disposing of waste is a major problem. Nobody wants to store this nuclear waste near their house, obviously. There have been proposals about storing it all deep underground in the central area. That hasn't really been widely accepted.
When we talk about different fuel sources that release greenhouse gases, what causes them to release that? Is it because if they're just a natural resource,
Yep.
and they're just underground or wherever they may be, what causes them to release it? Do they are they constantly releasing it?
So do you know where fossil fuels like coal, oil, natural gas are all considered fossil fuels? They're deep, they're underground somewhere. Do you know why they're there? Where do they come from?
These animals are just
Yeah, they came mainly from when the earth was covered in huge forests. Okay? Those, as they died and decomposed, they were trapped underground. Pressure from within the earth transformed them into these fossil fuels, which are very high in energy. So when those plants were growing, I don't know, we'll talk about this. What do plants absorb as they grow? They use sunlight, water,
Food.
That's what they do.
Air.
something else. What?
Oxygen.
Carbon
No.
dioxide.
Carbon dioxide.
You would
Oh!
So plants absorb carbon dioxide from the earth during photosynthesis, and they use it to grow. So that carbon dioxide has been stored by those plants millions of years ago and trapped there. But now,
They need some.
when we dig up those plants that have decomposed and burn them, that stored up carbon dioxide is now released into the atmosphere.
Okay.
And that's where it comes from.
Oh, you went to nuclear fission factory and you're putting it in a reactor. How would you get it? Are there times that really happens?
When you're handling it,
Particle
yeah, it comes enclosed in materials that absorb any neutrons and energy that are coming for them. And there's different types of fuel. They have to be purified and in different ways to make them, guys, to make them able to work in a nuclear power plant. And we'll get there in a minute. To make a nuclear weapon requires even purer nuclear fuel. And so we'll talk about that when we get to weapons. All right, there. So what we've been talking about is fission, taking fuels like uranium, a very, very large nucleus, allowing it to decay and split into smaller nuclei. Fusion, what does it mean to fuse things? To combine. And so nuclear fusion is when you take very, very small nuclei and fuse them together to a larger nucleus. Okay? And that process also releases large amounts of energy. In fact, fusion is where the energy from the sun comes from. In the sun, hydrogen is being fused together, forming helium, and in the process releasing huge amounts of energy in the form of light and heat, ultraviolet radiation, and so forth. Okay, here we have an example. If we take two types of hydrogen, fuse them together, form helium, and release neutrons in the process. So fusion takes place in the sun and other stars and releases huge amounts of energy. However, fusion generally requires very, very high temperatures. It's not something we can really recreate in conditions we could produce on Earth. If we could, fusion would be a wonderful source of energy because it doesn't produce radioactive wastes. It doesn't produce greenhouse gases either.
Wait.
Oh, can you go back?
It
Yep.
doesn't produce radioactive
Yep.
whatever
Waste.
yeah. Then how, like, what do you consider like ultraviolet rays? Are those like just there? What is
Yeah, no, those are harmful too, but not they're not radioactive.
Oh,
Yeah. So plasma is a state of matter that is often formed at very, very high temperatures, such as on the sun. And plasma consists of nuclei that have been sort of stripped of their electrons. And so these are the sort of conditions where fusion can happen. These sorts of conditions exist in stars. Nuclear fusion uses two types of hydrogen, two isotopes of hydrogen, usually, deuterium, tritium. Fuses them together, we decide to form helium and a neutron. Scientists would love to be able to find a way for fusion to happen at normal temperatures and pressures, sometimes called cold fusion. And cold fusion is sort of a dream that scientists have, because basically it could produce limitless electricity without releasing pollution.
can't like cold fusion take place in space? Because I saw something where it was like, if
Of course you did.
there was if there was some sort of element or something that hadn't been exposed to anything on Earth, or was just, something out there, and then it could fuse with something just because of like the immense pressure in space.
why can't
There's
you
not
watch
enough
Netflix
pressure in
and
space.
roll
I'm not sure about that. Generally, fusion happens in stars. And like we said, creates a large amount of energy in the process, but again, we can't recreate those conditions yet. Okay, it takes temperatures that are millions of degrees Celsius in order for that to happen. Sean? Oh, you can get hydrogen just from water. So you can take water, dissociation into hydrogen and oxygen, and use the hydrogen in the reactor. So if we were able to do this, it would be awesome. It would not produce dangerous wastes, guys. It can be controlled relatively easily by just removing the fuel. And basically we have an unlimited supply of hydrogen available. Problem is, at this point, it needs extremely high temperatures, and so there's not the technology yet to allow for cold fusion to But we have figured out one way to produce a fusion reaction, which we'll talk about in a minute. So where we have figured out ways of creating fusion have been in nuclear weapons. Okay.
Where's that?
So the first, we call that, what's another word for a nuclear weapon? Atomic bomb. Okay. So the first atomic weapons were developed by what country?
USSR.
Nope.
Japan.
Nope.
Germany.
Nope.
Wait,
America.
By the United States. The
Yay!
United States were the first, was the first country to develop nuclear weapons. In around the time of what war?
World War I. World War I.
In World War II, the idea
pronounce it right.
or the concept behind nuclear weapons started to be refined by scientists. And so basically people understood you could make a weapon out of this nuclear material, and there was sort of a race to see who was going to develop the first nuclear bomb. Okay? And so in the United States, the government brought together scientists from all over the United States and all over the world to work to put together and refine the technology to produce a nuclear weapon. And the U.S. was the first country to develop a nuclear weapon, okay, and also to use a nuclear weapon. So nuclear weapons were used at the end of World War II when the United States dropped a nuclear bomb on Hiroshima and Nagasaki. The bomb dropped on Hiroshima. They were both fission bombs. They used the first one, little boy, was dropped on Hiroshima, used uranium-235 as its fuel source. Okay, it had basically a conventional explosive. Okay, that sent a bullet of uranium down this long tube that hit more uranium at the end, causing the chain reaction to begin. So the other type of fission bomb was dropped later on Nagasaki. This was a different design. They had a spherical conventional explosive with uranium and plutonium in the middle, and the conventional explosive forced the plutonium in, okay, to the center, and that caused the chain reaction to begin. So these weapons release unbelievable amounts of energy and basically destroy any living thing within a very large radius. This is, I believe this is Hiroshima. This is before the bomb was dropped. This is the exact same place, okay? All right, it's not really funny though, because millions of people died of it. So, not something to really laugh at. This is what the area looks like 1,000 meters, 2,000 meters out, where basically every single building just completely leveled. Okay? And also, the results of this, the radiation poisoning, contaminated the area, resulted in people, even the people that did not die in the initial explosion, developed cancers and radiation sickness that lasted long after. There are also fusion bombs that are produced. They have not been used. These are sometimes called hydrogen bombs, and they use fusion rather than fission. And basically these bombs fuse isotopes of hydrogen to create helium and a huge amount of energy. These are much, much more powerful even than the bombs dropped in Japan, the fission bombs. Now, it requires very high temperatures, as we talked about, in order to start the process of fusion. So the way that they work is there's actually a fission bomb inside that starts the reaction, creating these extremely high temperatures, which then starts the fusion bomb and then detonates the fusion bomb. So it's a combination of both, resulting in a much more powerful explosion. Okay, so this is to give you, these are, the Sara bomb is in relation to, so this is Mount Everest, okay? This is the tallest tower in Dubai. This is the size of the cloud formed after the detonation of the bomb over Hiroshima. This is what the modern fusion bomb looks like. Many times the size, or 5 times greater than the bomb dropped on Hiroshima. So we have developed huge nuclear weapons. They can be delivered on missiles, from submarines, from aircraft, from land, and there's a lot of there's a lot of controversy about nuclear weapons. Countries come to agreements to limit their use of nuclear weapons. There are treaties and agreements to prevent other nations from obtaining nuclear weapons. And so some of those things are things you'll read about in the newspaper and so forth. Let's finish up with this slide. There's also something called a neutron bomb. It's basically a version of a hydrogen bomb, okay, that doesn't produce a huge explosion, but does release a large amount of radiation. So it kills living things, but does not completely destroy all of the buildings like the fission bomb did. Okay? That's because the neutrons collide with protons in living tissue. They break down chromosomes, destroy cells, especially in our nervous system. Okay, so this is a deadly bomb that doesn't have the same sort of explosive capability that the other bombs. All right, so tomorrow we'll go over your homework and we'll review for our quiz. And then we're going to move on into a second grade unit after that.